Hello friends, welcome back to my channel. Today I would like to share with you some of the concepts from intermolecular forces, electronegativity and bond properties. Let's first look at bond polarity. Bond polarity is determined by the difference in electronegativity. Nonpolar covalent bonds. A nonpolar covalent bond is a covalent bond in which the bonding electrons are shared equally between the two atoms. In a nonpolar covalent bond, the distribution of electrical charge is balanced between the two atoms. Here gives an example of chlorine molecule, which is nonpolar covalent bonding. Its electronegativity difference is given as 0. Molecules in which the electronegativity difference is very small also are considered nonpolar covalent. An example would be a bond between chlorine and bromine. Polar covalent bonds. It is a covalent bond in which the atoms have an unequal attraction for electrons, so the sharing is unequal. In a polar covalent bond, sometimes simply called a polar bond, the distribution of shared electrons within the molecule is no longer symmetrical. In the polar covalent bond of HF, the electron density is unevenly distributed. There is a higher density near the fluorine atom and lower density near the hydrogen atom. An easy way to illustrate the uneven electron distribution in a polar covalent bond is to use the Greek letter delta along with a positive or negative sign to indicate that an atom has a partial positive or negative charge. The dipole moment is a measure of how polar a bond is. The direction of the dipole moment is shown by the following sign, in which the arrow points to the partially negatively charged end of the dipole. Assigning polarity to molecules. To determine whether a molecule with more than two atoms is polar, the following things have to be taken into consideration: the polarity of each bond, how the bonds are arranged in the molecule. Some molecules have polar bonds but are overall not polar because the polar bonds in the molecule are arranged in such a way that the individual dipole moments cancel each other out. For example, carbon dioxide is a linear molecule. The oxygen atoms are more electronegative than the carbon atom, so there are two individual dipoles pointing outward from the carbon atom to each oxygen atom. However, since the dipoles are of equal strength and are oriented in this way, they cancel each other out and the overall molecular polarity of carbon dioxide is 0. Another example, water is a bent molecule because of the two lone pairs on the central oxygen atom. The individual dipoles point from the hydrogen atoms towards the oxygen atom. Because of the shape, the dipoles do not cancel each other out and the water molecule is polar. In the figure below, the net dipole is shown in blue and points upward. Some examples of polar and non-polar molecules with various molecular geometries is given here. Under polar molecules, HCl, NH3 and CH3Cl. For non-polar molecules, BF3 and CCl4. The next subtopic is intermolecular forces. Covalent and ionic bonds can be called intramolecular forces, forces that act within a molecule or crystal. Molecules also attract other molecules. Intermolecular forces or van der Waals forces are attractions that occur between molecules. Intermolecular forces are weaker than either ionic or covalent bonds. However, the varying strengths of different types of intermolecular forces are responsible for physical properties of molecular compounds, such as melting and boiling points and the amount of energy needed for changes in state. There are two types of van der Waals forces or intermolecular forces. The first one is instantaneous dipole induced dipole forces or temporary force. This is also called London dispersion forces. The second one is permanent dipole forces, including hydrogen bonding. Let's first look at London dispersion force. London dispersion forces are the weakest type of intermolecular bond. They exist between all atoms and molecules. These are caused by an uneven distribution of electrons within an atom. This results in a slightly negative and slightly positive charge on either side of the atom. A temporary instantaneous dipole has been established, which can induce a temporary dipole on the neighboring atom or molecule. London dispersion forces are the electrostatic attraction set up between the slightly positive end of one atom or molecule and the slightly negative end of the other atom or molecule. These opposite charges then attract each other. As you can see here, random fluctuations in the electron density within the electron cloud of a helium atom results in a short-lived or instantaneous dipole. The attractive force between instantaneous dipoles and the resulting induced dipoles in neighboring molecules is called the London dispersion force. The strength of London dispersion forces depends on the size of the molecule or atom. Larger atoms and molecules have more electrons. This leads to a larger dipoles being established. Permanent dipole interactions. Molecules with a permanent dipole are polar. Polar molecules display attractions between the oppositely charged ends of the molecules. This type of intermolecular bond is stronger than London dispersion forces with the same number of electrons. As you can see here, dipole-dipole forces result from the interaction between the positive end of one dipole and the negative end of the neighboring dipole. Dipole-dipole forces are similar to ionic bonds, but because they involve only partial charges, they are much weaker. The next bonding is hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular bond. It is a specific type of permanent dipole to permanent dipole attraction that occurs when a hydrogen atom is covalently bonded to a highly electronegative element such as nitrogen, oxygen, or fluorine. As with permanent dipole to permanent dipole attractions, the oppositely charged ends of molecules attract. As you can see here, a hydrogen bond in water occurs between the hydrogen atom of one water molecule and the lone pair of electrons on the oxygen atom of a neighboring water molecule. Ice is less denser than water. This is an application of hydrogen bonding. In the liquid state, the hydrogen bonds of water can break and reform as the molecules flow from one place to another. When water is cooled, the molecules begin to slow down. Eventually, when water is frozen to ice, the hydrogen bonds become more rigid and form a well-defined network. The bend shape of the molecules leads to gaps in the hydrogen bonding network of ice. Therefore, ice has a very unusual property that its solid state is less dense than its liquid state. As a result, ice floats in liquid water. Here is the picture representing the bonding in water and bonding in ice. So that's all. Thank you so much for watching.